Welcome all of you for the topic of precision rectifier. Rectifier, we know what is rectifier. Convert AC to DC. Convert AC to DC, that is called rectifier. So which one it will going to convert? So AC power it will going to convert into DC power. Why I needed for DC power? Because I need to charge my mobile phone. So I need to charge my mobile phone. So that's why I needed for the rectifiers. Okay, so then what we were seen in that previous topics, so half wave rectifier, only half cycle, positive half cycle only conductor, or you may be designed, okay, or negative half cycle only you want to conductor means, so connect the diode in reverse directions, only negative half cycle only conductor, because it's a arrow mark, it is simply arrow mark. Okay, so you can design about that one, only half of the cycle is conducted, that's why it is called half wave rectifier. And full wave rectifier means what? Both positive magnitude as well as negative magnitude, both magnitude, okay, both is a magnitude. I mean, entire one cycle is converted. That is called it is a full wave rectifier, and followed by full three phase full wave rectifier also we were seeing. So this is a diagram. What is this diagram? This is a half wave rectifier. I have shown you half wave rectifiers. So for example, okay, it's a phase with respect to neutral. Only the current is a flow. Whenever okay, top is a neutral with respect to bottom is a phase, so neutral with respect to phase, the current is doesn't flow, the diode is in a open bias, okay, at the time. Okay, if you want to reverse that, you will going to connect it as an opposite means only negative half cycle it is going to connect it. So that's why I'm said about coming to the point as per the given circuit. So it is a phase with respect to neutral, positive half cycle it is conducted during the negative half cycle, bottom is a phase with respect to neutral. So phase it's a current is a flow this side, so the diode is open cycle, open switch, so the current is not flow during the negative half cycles. So I okay, then so this is a half wave rectifier what we were discussed. Okay, so positive half cycle only conducted, negative half cycle is a 0. Okay, then this ideal characteristics is in characteristics, not in practical. So ideal characteristics, okay, no loss. What about practical characteristics? So this is a threshold losses take place. What is the threshold? VT, voltage drop across the diode. Due to the voltage drop across the diode, okay, for example 0.7, okay, for example silicon means 0.7, so 0 to 0.7 is a okay, no output voltage. 0 to 0.7 is a no output voltage. After 0.7, then only output voltage is produced. That is called a threshold voltage. 0 to 0.7, no output voltage. Okay, this diode is a okay. Diode rectifier is a okay for your battery charging application. That all things is okay. Whenever you are going for that very small type of the applications, signal conditioning systems, small signal conditioning systems, or you have going to go for the demodulation type of the signal conditions, at the time that 0.7 voltage also important. So you see the input is applying that 1 0.1 0.2 0.3 0.4 0.5 0.6 0.7, but what about output? 0. After 0.7 only that output is a produced. Some diode is a 1 volt voltage drop. So up to 1 volt no okay, no output voltage. So like it is a consumed, that threshold value is important for my application, small signal conditioning application, demodulation type of applications. It is very important. Then what to do? That is a question. How to minimize that 0.7 threshold voltage drop? This ones, how to minimize means, so in okay, before the diode, okay, in front of the diode, okay, this is a point, or between the source and the diode, between here you will going to put one circle. This is a point, what you will going to connect it? One operation amplifier you can connect it. One operational amplifier you connected between source and the diode, between you can connect it. Okay, the differential amplifiers you may be studied. Okay, for example you can look this ones. So here is what is the source to the diode to the load. This is the previously you were seeing here. See, source to the diode to the load. Yes, source to the diode to the load. It is a previously, but between here what I have connected, actually this is a ground, this is a ground, it's nothing but it's a joint. Okay, between the point here I will going to connected one operation amplifier, differential amplifiers. Okay, plus minus, there are difference of the two signals. Okay, minus it is going to closed type of that one output. Okay, this is the operational amplifier output. The output is connected okay, connected to that second input. So like I have connected one operation amplifier. Okay, so now it is called a precision rectifier. It is act as the precision rectifier at a 0.7 voltage drop. Okay, threshold voltage drop also minimize. Okay, it is start with the origin. That's all. So this is the purpose you are going for that precision rectifier. Then what you will going to further you will going to see. So you will going to, if it is a mode 1 mode 2 condition, okay, if it is a switch on, okay, under switch off condition, there are two conditions. Or what is the mode 1? So phase with respect to neutral, another one is a neutral with respect to the phase. So when, okay, up is the phase with respect to neutral. So like we will going to see about the two mode conditions. Okay, so let's we're going to see. So if it is a phase with respect to neutral, so phase with respect to neutral, now I will going to flow the current is a flow, so greater than 0. So greater than 0. If it is a up is a neutral with respect to phase means less than 0, just opposite. Now okay, less than 0. So now I will going to apply the, okay, greater than 0 phase with respect to neutrals. When I will going to apply, what about output voltage? That is the question. When I will going to apply the phase with respect to neutral or greater than 0, what is the output voltage? That is the question. See, when I will going to apply that once, okay, that is a, okay, greater than 0 voltage. So here is the greater than 0. It will going to voltage is flow. So when it is a voltage is a flow, here this is a differential amplifier or operation, okay, op-amp you can say. So it will go to two input, difference of the two input. So difference of the two input is the input, then output is the V naught dash. What is that one? Output okay, what is that one? Generally, okay, operation amplifier you can say, take it, output V naught dash CD is equal to gain multiply input differentiation. This is the things. Output of the operation amplifier, it is equal to gain, okay, this is called gain multiply difference of the input voltage. This is about that operational amplifier output. What is operational amplifier output? V naught dash, it is equal to gain multiply difference of the two input. Yes, this is the things. Okay, so operational amplifier output is a V naught dash. Okay, then next one, 0.7 voltage is a drop, it will going to consume for that diode. Then remaining is here, it is a point, this is a node, this node is called V naught. So V naught it will going to produce. Okay, so here V naught dash, it is equal to 0.7 plus V naught, 0.7 plus V naught, that V naught is a here flow. So V naught dash, it is equal to, V naught dash means this is a point, it is equal to, for example, these two is connected in series. So here is your father up to here is a 50 rupees giving. So this is a, you are consuming for that 7 rupees. So here is a, you will go to consume the remaining is a resistor consuming 43 rupees. So summation of the 7 rupees plus 43 rupees, it is equal to, so 50 rupees. So input here at the point of input, this is a point of input, this point. So okay, V naught dash, it is equal to V naught plus 0.7 volt. Okay, so now what I will going to do, this V naught value I will going to substitute it to in these equations. Yes, I will going to substitute it. So this is a V naught place, I have to replace into the V naught plus 0.7 volt. So this is a multiply with these parameters. So I will going to move this gain on the another side. So gain will come here. So it is equal to, so V plus minus V naught, V plus minus V naught. Generally the gain values very higher, the gain values higher. So this is a value very less compare, okay, numerator is less than the denominator. So the output value is 0. So the output value is 0. Why it is 0? Denomination is gain is higher compared with the numerator. So that's why it's a 0. So 0, it is equal to V plus or V minus, or V plus you can keep it, then V minus you can move opposite side. So V plus is equal to V minus, that is called output. So during this condition, simply say whatever you are going to apply the input, it is coming to the output as it is the previous conditions. As it is the previous condition means as it is the diode rectifier, whatever you are going to apply here, it is coming to the load. That's all. Whatever you are going to apply the input, so it will come as an output. Okay, but okay, that is called the output. So this is about mode 1 operations. So phase with respect to neutral, RG greater than 0. So here what is about, this is called the open loop gain. Another one is denominator is high, gain is value is high, so high, that's why it is coming as a 0. Okay, 0.7 voltage drop. Okay, the silicon diode is using 0.7 voltage drop is happens. So we will going to move on with the mode 2 condition. What about the mode 2 condition? So less than 0. So during the less than 0, what about the case? So if it is the less than 0 conditions, so for example, okay, neutral with respect to the phase. So phase value to this move, okay, it is the diode is opposite direction, so diode is the open bias. So now diode is the open bias. Okay, so due to the diode open bias, the circuit is not closed like that one here. So you will go to, it's a, okay, what about here? Previously, okay, greater than 0. Now it is a less than 0. Input is less than 0. So less than 0, below 0. So below 0. So below 0 means, so here is the input is below 0, so the output also 0. So 0 is a flow to here. Okay, here also 0 voltage. So when it is like it is a comparison, here is a V0 dash, it is a produce, V0 dash is produce. Okay, like it is the mode 2 conditions. So during the conditions, so it is operational amplifier is an open loop. Operational amplifier, it is act as an open loop, because you can see that one, it is a open the circuits. Okay, the diode is a reverse bias. So when less than 0 value is going, so it is opposite direction. So the diode is a reverse bias. So V0 are the operational amplifier output also. Okay, what will happen? This one also automatically negative. So this is a mode 2 conditions. Okay, let's see, we're going to draw about that waveforms. So waveform is one is a mode 1, second one is a mode 2 conditions. Mode 1 diode is a forward bias, mode 2 diode is a off switch. It is a not a conducting. So it's a reverse bias, it is a off. So mode 1 is a greater than 0. Okay, the output is there. What is the output? Output is equal to input. So you are getting the same waveform or not? So output is getting the input. The same similar to that off wave rectifier. Similarly, output is equal to input. Mode 2 condition diode is not working. So it is a 0. Okay, so this is about that precision rectifier waveform. Okay, precision rectifier. Next one, okay, this precision rectifier also it has one limitation is there. The precision rectifier, there are two in that slide. It is showing there are two limitations. Okay, one of the major limitation is that. What is the one of the major limitation means? So this precision rectifier, okay, whenever operate high frequency, it will get that distorted. So it will get the distorted. So how to avoid the distortion? So this is one of the major point about the limitation. It will going to operate for the 50 to 100 Hz. Whenever you are going for the 50 kilohertz to 100 kilohertz, so what will happen? Whenever higher frequency it is, it will going to get the distortions. This is the one of the point. Okay, then second point, okay, here is what they are given. It will limit the maximum operating frequency. Precision rectifier is limit the maximum operating frequency, okay, of the rectifiers. Okay, if you want to increase the operating frequency, what to do? That is the problems. Okay, this is one of that limitation. What is one of the limitation? Whenever higher frequency, when you are going to go, so it you going to get the distortions, it is going to get distorted. Then second one small limitation means mode 1, what about that one? Output is a positive saturation. Mode 2 is what about that one? Negative saturation. Okay, this is a positive saturation, negative saturation. Okay, across that V0 dash. So V0 dash across positive saturation. Okay, V0 2 dash across negative saturation. Okay, negative saturation is occurs. Again, mode 1, when you go positive saturation, this is a time gap between the mode 2 to mode 1. It will take some time gap. The time gap also, it is one small limitation. It's not a big limitation. Okay, when it is moved from the mode 2 to mode 1, the time gap. So negative saturation to positive saturation, it will going to move. So it is taking time to move from negative saturation to positive saturation. It is one of the small limitation, but it is not a biggest one. One biggest limitation you can say, it does not operate on the higher frequency, distorted. Then what to do? That's why you can go for the precision rectifier. So what is a precision rectifier? The same previously you had seen about the rectifier, but okay, what is that one? Precision rectifier. Modified precision rectifier, you will go for that one. Modified precision rectifier. Okay, here sorry. Okay, modified precision. What is a modified precision rectifier? So here is added one more diode is added. D1 also here added. So previously you were seen about here is added D1. Another one is previously you will going to apply the input here. Now you are going to apply the input here. So negative point you will going to apply the input, that is okay. So here is a diode, is one more diode is added, and the resistance also you are added. Previously no resistance here, so now resistance as well as diode is there are two parameters you are added. Okay, so when you will going to add it to, okay, when you will going to add it to, you will going to minimize in the limitation of the previous one. So how to minimize the other ones? So first one, there are two diodes, diode D1 and D2. There here also there are two mode 1, okay, mode 2. What is mode 1? V in greater than 0, mode 2 V in less than 0. So V in greater than 0, V in less than 0. So now it is a reverse conditions. Okay, just a reverse condition means what you can say, okay, what precision rectifier you are seeing, output voltage is equal to input voltage in mode 1. Now output voltage is equal to 0. In mode 2 condition, what about that one? V in less than 0, output voltage is equal to minus R2 divided by R1 into V in. So this is the values produced. So previously output voltage is equal to input voltage, then V0 is equal to 0, just it is a reverse. So here is mode 1 0, mode 2 it is a value R2 minus R2 divided by R1 into V in. Okay, there are two mode operations. Mode 1 conditions, there are D1 is on, D2 is off. Okay, D2 is off. So when D2 is off means the operational amplifier is act as in the open loop. Vout is equal to 0. Vout is equal to 0. It is a open loop. So it is working up to here, but here is a V2 is no V2. So Vout is equal to 0. During the mode 2 condition, what about the mode 2 condition? So here is a remote. D1 is off, D2 is on. Okay, D2 is on. So due to D2 on, so V output is equal to okay, okay, what about that V in under these two resistance, V in under these two resistance, V in multiply R2 divided by R1. So it's a negative saturation, so minus. So this is a like we will going to develop. So we go to a little bit deep. So V, okay, first one mode 1 conditions. So V in greater than 0. So when V in greater than 0, okay, here is a D2 is remove the D2. Here no D2. D2 is a reverse bias. So what will happen? So V in greater than 0, it's a flow from that power, okay, through that diode D1. It will going to reach here. So reach it will going to here on that once. Okay. But if the diode is no diode is there, so no diode, so it is the power, I mean current is okay, negative. This is a negative value, so 0 voltage, so 0 voltage of that one. So this is a drop across that diode, so minus 0.7 voltage drop, minus 0.7 voltage drop. So due to the no diode, okay, so it is not reach here. So here is a maintain the 0 voltage. Okay, when mode 2 condition, what about the mode 2 conditions? Mode 2 conditions, so here it's a equivalent circuit diagram is showing. So in that mode 2 conditions, so diode is conducting, D2 is conducting, D1 is open switch, D1 is a open switch. The output is equal to V0 is equal to, what about that one? So input multiply with these two resistance. What about these two resistance? The ratio of these two resistance, R2 divided by R1. When you will going to apply the 0 voltage KCL, when you will going to apply the 0 voltage KCLs, so you will going to, okay, at the mode I have written the KCL value. So input, what about the input? Negative point here is a negative input, that's why minus V in divided by R, okay, it is equal to, so V out divided by R2. Okay, at node 0 voltage I have written. Why I have mentioned minus means because it is connected to that operational amplifier minus. So if it is plus means plus, so it is connected to the minus. So okay, entering current it is equal to, okay, so entering current is equal to existing current at the node point. So at the node point, okay, okay, entering current it is equal to existing current. What about here? I is equal to V by R. What is the I? I is equal to V. V is what is that one? V in divided by R1. So it is connected to the negative. So minus. It is equal to, here is what is that one? I is equal to V by R. V out divided by R2. Okay, V out divided by R2. So rewrite the equation. V naught it is equal, V naught equal only you can keep it. So R2 you can come this side. So minus V in multiply R2 divided by R1. Yes, that's why the equation is derived. The came. Okay. So do you know KCL? KCL is equal to entering current is equal to existing current at a node. Okay, 0 voltage. Okay. So this is a waveform. So what is the waveform of that ones? So here is a, so V in is equal to greater than 0, mode 1 condition. It is a, what about that one? Input is a blue color, then output is a what is the color? It is called a yellow color. Okay, so here is a input is a, okay, mode 1 condition, our output is equal to 0. Mode 2 conditions, okay, output is a produce. What is output is produce? V in multiply R2 by R1 minus R2 by R1. Okay, so like the waveform is produced. During that year mode 1 condition, V in greater than 0, what about that one? 0, 0. What about next one? Mode 2 condition, minus side, okay, negative side, R2 by R1, okay, R2 by R1. So this is the thing. Suppose I will going to change the direction of diode, means what it will happen? So it will come like, okay, that's all. So this is about modified precision rectifier. So modified precision rectifier you can use to, you will going to increase the, okay, operating frequency. Okay. Next one, precision of the full wave rectifier. What is the precision of the full wave rectifier? It will going to connected. Okay, well, okay, it will going to connected off wave rectifier. Just now we have what we were seeing. The gain of the off wave rectifier is minus 2. The gain of the off wave rectifier is minus 2. It will going to adder. So you will going to one adder you will going to use. Okay, like you will going to connect it. So due to that ones, so you will going to see that one. So due to that gain values double times of the gain. So here is the okay, it's a input waveform off wave rectifiers. Okay, minus 2. So it is a double times. So double times. So summation of this is a waveform is you will going to get it on the summation of that one. So that's why it is called a precision full wave rectifier. Precision full wave rectifier. So coming to the end summary, what is that one? Precision rectifier. Why do you want to go for precision rectifier? The diode rectifier, it is not suitable for that is small signal condition type of the application. It is not suitable, and demodulation type of the application not suitable. That's why you will go for that precision rectifier. Okay, precision rectifier means what? The same diode rectifier. So before the diode you will going to add the one operation amplifier. Okay, so mode 1, mode 2 conditions you are seeing. Then next one, modified precision rectifier. Why you move to the modified precision rectifier? So precision rectifier, it has a drawback. The drawback of that one is it is not suitable for that higher ranges of the frequency. So that's why you can move for that modified precision rectifier. So it is not suitable for higher ranges of the frequency. So 50 to 100 kilohertz range frequency is not suitable. So that's why you can go for that modified precision rectifier. Modified precision rectifier means one more diode and one more resistance is present. So with the help of the diode and resistance, okay, it will go to operator mode 1 and mode 2. The next one, full wave precision rectifier means, okay, off wave rectifier, it's a 2 minus 2, gain of the off wave rectifier minus 2, okay, plus adder you will going to use, so you will going to get the full wave. That's all. Thank you for the class attended.